Hi. I'm Jim Heffron. These are my lessons in Calculus 1. So this is the first videos where we're talking about the homeworks. As we go through the sections, I'm going to do, for each section, I'm going to do a collection of homeworks. I often do 5. That's kind of the nominal number because that's the number I talked about in how to study for mathematics classes. But I sometimes will, if the problems are longer, sometimes I'll do fewer. Once or twice, I think I may do more. You'll notice also that when I go through and do these, that although you should do every part, I may just do one part and leave the rest for you. So for one of the problems today, for example, I'm only going to do one part and there's more than one part. The other thing that I wanted to talk about, other than kind of the general setup of where we are, the other thing that I wanted to talk about is peaking. So the idea is if you have problems with one of the questions, or maybe more than one of the questions, if you have problems with one of the questions, you should give it a fair try. I mean, give it an honest try. But if you're stuck, if after 2 or 3 minutes, you just, I don't see what to do. What am I supposed to do with the capital G? Fair enough. You should have a look. I mean, don't walk around going, oh my God, I must be an idiot. Just, have a look. So have a look could mean several things. Have a look could mean flip back through the section of the book, trying to find an example that's like the one that's given you trouble. Having a look could mean going back on the slides that I have for that section, all perfectly fair. And having a look could also mean going on some AI and asking the AI, give it some appropriate prompt like show the work that I would need in order to solve this problem. All those things are all fine, although I'll say that with the AI, you have to be a little careful. Sometimes gives the wrong answer, sometimes gives an answer that's only a little bit wrong, so it's mostly right. Got the right answer, but there's something funny in the middle, so you have to be a little more careful with AI than you'd have to be with the textbook. But nonetheless, can be a useful tool. Those things are all great. So you should feel free to peek. That's absolutely fine. But you should also, the absolutely wrong thing to do is to read the question and then immediately ask AI the answer. How do you do this problem? Or look in the book for the answer. Instead, you should give it an honest try until you understand what it is that's giving you trouble. Oh, the logarithm is giving me trouble. Or I just don't see when I have the square root. What am I supposed to do with at that point, then you're ready to see the answer, and having a peek makes all the sense in the world. Okay, very good. So you'll notice that when I do these problems that I often, in fact almost always, will include a problem from an earlier section. On today's problems, the earlier section is 1.5, which I actually don't cover in class. I don't cover chapter 1 in class. So I reach back to something that was before. The idea there is, as I described in the video on how to study mathematics, the idea there is just simply that you got to keep bringing it up. You got to keep recalling it. The way that memories are made firm is by continually going back, regularly going back, every week, every other week, every third week, regularly going back and revisiting that material. And then when you come to the exam, you'll see a question and you go, huh, I know that. That's a good feeling. Okay, all right, very good. So on we go here. Let's have a whack. So just to remind you here of what you saw at the beginning. So the problems listed are, it says section 1.5, number 47, and then in section 2.2, the section that we're doing, I'm going to do an example that's in the book, and then 3 questions from the homework that were assigned on the homework sheet that I've included among the files that are uploaded. So you could have a look at what questions that I asked when I assigned questions for this class. Okay, all right, so let's see then. I want to bring up the document camera. There we go. And I'm going to start in on the problem. So let me see how I do. And I'll apologize in advance for my handwriting. Okay, so it says it says section 1.5, question 47. Oops. Didn't quite make it. There we go. Section 1.5, question 47, and it says use formula 11 to evaluate the expression. I'm only going to do part A. Once you've done part sort of, you can do part B on your own. So it says log base 5 of 10, and in particular, it says use formula 11. So I'm going to have to flip back a couple pages to find formula 11 to remind myself what formula 11 says. Formula 11 is one of the formulas that I ask people to memorize. Oops, needs a little light here. There we go. Formula 11 is one of the formulas I ask people to memorize about logarithms. Log base b of x is natural log of x over natural log of b. Okay, so I'm going to copy that down to my page so that I don't forget it and find myself back again. Okay, so let's see. Let's have a look. So formula 11 is that log base b of x, log base b of x is log base, natural log base e of x over the natural log of b. Just as a comment, just to say, that's the same thing, of course, as 1 over the natural log of b times the natural log of x. In other words, log base b and log base e are proportional to each other, and here is the constant of proportionality. Log base b, 1 over log base b is the constant of proportionality. Okay, the question specifically asked for log base 5 of 10, so log base 5 of 10, and of course I'm just plugging into the formula is the natural log of 10 over the natural log of 5. And it's just a question of pulling out a calculator and punching it out. And I'm going to actually do that if I can make the darn thing show up here. Let's see. Is that bright enough? I think that's okay. So I'm going to take natural log of 10, 2.30258. So 2.30258. 1. Now, normally you don't write all the decimal places, but sometimes when I do calculators in class, I like to write all the decimal places so a person can feel confident that they punched the same numbers. And then natural log of 5 is 1.6094, 1.6094379. And then I won't bother you with doing the division. You just simply punch the divide by sign and you're done. Okay, so the first question is just a straightforward application of a formula, although it's a formula that's very important because it says that all logarithms are proportional to each other. Okay, anyway, that's the first question. Second question is example 7 in section 2.2. So I got to pull out example 7 in section 2.2. Let's see if I can find that darn thing. Example 7, there it is, in section 2.2. Calculator out of the way. There we go, example 7. Okay, and I picked this example actually because there's something a little bit peculiar about it. So it says, does the curve 2x over x minus 3 have a vertical asymptote? To show that something has a vertical asymptote, what you have to show is that either the limit, we're gonna show, of course, that there is a vertical asymptote at x equals 3. So you have to show either the limit as x approaches 3 is infinity or minus infinity, or the limit as x approaches 3 from the left is infinity or minus infinity, or the limit as x approaches 3 from the right is infinity or minus infinity. Any one of those 6 cases will do, and you'll notice that the book actually showed 2 of them. So a little bit peculiar. The book only need to show 1. Didn't need to show both limit as x approaches 3 from above and limit as x approaches 3 from below. You could just show one or the other. So I'm going to do that. Going to be a little bit lazy and only going to do one of them. So I read the example statement and I put the book down. I can peek if I get stuck, but I put the book down and I'm looking to show that the limit as x approaches 3, I'm going to show from below of 2x over x minus 3 is infinite. One of the two, plus or minus infinity. Okay, and we're just doing this simply by arguing with words. That's all. We don't have anything else at this point, but in any event, I'm just arguing with words. So as x approaches 3 from below, 2x approaches 6. X approaches 3 from below. The numerator, 2x approaches 6. It actually approaches 6 from below, but it doesn't actually matter to our argument. And as x approaches 3 from below, the denominator approaches 0. As x approaches 3 from below, approaches 0 from below. So we know that when we have a constant, the top is basically constant. When we have a constant on top and numbers that are getting closer and closer to 0 on the bottom, we're going to go infinite. Because, for example, if you divide by 1/10, that's the same thing as multiplying by 10. If you divide by 1/100th, invert and multiply, it's the same thing as multiplying by 100. Divide by 1/1,000,000th, that's the same thing as multiplying by 1,000,000. So the top is staying pretty much at 6. The bottom is causing the fraction as a whole to be multiplied by 10, 100, 1,000, etc. And all we got to worry about is the SIGN. So the sign, the SIGN, the top of the fraction is going to be plus, positive, because it's hanging around 6. It might be a little less than 6, but it doesn't matter, still positive. The bottom of the fraction, however, will be negative. That's what the minus here. So the bottom, so top numerator is positive, about 6, and the denominator is negative, about 0. So the result is the fraction as a whole approaches minus infinity. So that makes 3 an asymptote. The problem with asymptotes are that they're very hard to spell. Okay? Okay, and then now we're going to the homework. Next up is going to the homework, and I am just simply flipping to the homework section. It's number 5, 15, and 31. You'll notice that I didn't pick the first 3 homework questions. I picked ones sort of scattered throughout the homework because I'm trying to illustrate how you might do the different types of problems. And again, you also noticed that I would feel free to do sort of one part instead of many parts, sort of thing, if it's helpful. Okay, trying to make good use of the time. So I'm looking through the homeworks, and I'm simply going to go to 5, 15, and 31. Those all are homeworks that were assigned, but I'm sort of skipping around because I think it might be useful. Okay, so let's see number 5. I actually need the book for number 5 because I have to point to something. Let's see here. I don't want to point with my pen because I don't want to get it on the... All right. So it says, for the function f whose graph is given, can you see the graph is here? For the function f whose graph is given, state the value of each quantity if it exists. If it doesn't exist, explain why. Anyway, we're just supposed to give some vague indication of what's going on. It says the limit as x approaches 1 of f of x. So here I am, there's x equals 1. And when x is near to 1, not necessarily equal to 1, but when x is near to 1, then the output, the red curve, is near to 2. So this is just not too surprising because it's the very first question. This is, it's only number 5. This is limit as x approaches 1 of f of x equals 2. Simply because there we are, when x's are near to 1, then the output y's are near to 2. Next up, it says limit as x approaches 3 from below. There's also a limit as x approaches 3 from above. And then over here, it says limit as x approaches 3. And finally, it says f of 3. So the real action here is happening at 3 right there. The limit as x approaches 3 from below for numbers that are less than, slightly to the left of, but not equal to 3, you can see that the outputs are very close to y equals 1. So the limit as x approaches 3 from below is 1. Limit as x approaches 3 from above, when outputs are close to 3 but slightly above, when inputs are close to 3 but slightly above, then outputs are close to, actually slightly below, but close to 4. So when inputs are close to 3, not equal to 3, slightly above, you're looking at outputs that are close to 4. So the limit as x approaches 3 from above of f of x is 4. And finally, it says, what's the limit as, what's the limit as x approaches 3 of f of x? And the answer is not defined, does not exist, DNI. in my class, I take all those things as acceptable answers. So that's because this exists, but they are not equal. So I would say here D and E. So again, some people are going to want you to say not defined or all fine, but the point is that there's those part B and part C have to equal each other. And finally, E, f of 3. Well, there is a value for f of 3. When x is 3, the output is y equals 3. So f of 3 is defined, but the limit is not defined. So again, the limit is not about f. You don't just plug in. The limit is not about 3 in this case. The limit is not about the anchor point. The limit is about being near to the anchor point. So the point of this question is to try to illustrate exactly that sentence. Okay, good. On to number 15. Oh, if I can get it on the screen. There we go. My goodness, the book weighs a lot. Sketch the graph of an example of a function f that satisfies the given conditions. And I'll read them, but then I've got to move it away to write on the paper. So it says they want me to sketch a graph where the limit as x approaches 1 from below is 3. The limit when x approaches 1 from above is 0. And f of 1 is 2. So again, limit when x approaches 1 from below is 3. Limit when x approaches 1 from above is 0. And f of 1 is equal to 2. So the action is happening at 1, and they want us to do sort of 3 different things. Okay, so this is number 15. Move the page up. There we go. Number 15. So I have the limit as x approaches 1 from below, the limit as x approaches 1 from above, and f of 1. So I got to include 1, that's for sure. And I'm going to need 1, 2, 3. I want the limit as x approaches 1 from below of f of x to be 3. So I'm going to, why not? I have a red pen. Why don't I do that? I'm going to do this. Okay, so when f approaches 1 from below, it's heading toward a value of 3. The limit when x approaches 1 from above of f of x is 0. So when you're approaching 1 from above, 1.1, 1.01, 1.001, the outputs are tending to be 0. Of course, the open circle means that it doesn't include that point. And what they want is that f of 1 is equal to 2. So I need a closed circle to indicate that f of 1 is 2. Okay, so same point. This question is trying to make much the same point as the one that we previously did. But in this case, instead of giving you the graph and asking you facts about it, here they're giving you facts about it and asking you the graph. So, it's not the slickest math trick in the world, but it's a math trick that's supposed to help a person figure their way through what limits are about. Okay, last one is number 31. So let's pick number 31 and see what we're looking at here. There we go, number 31. Number 31 says the limit as x approaches 2 of x squared over x minus 2 quantity squared. The limit as x approaches 2 of x squared over x minus 2 quantity squared. Okay, and so we're supposed to figure out what is happening here with this particular limit at x equals 2. Okay, so why don't I write that down? 31. Limit as x approaches 2. Make sure I copy the right one. Limit as x approaches 2 of x squared over x minus 2 quantity squared. Okay, and it seems to me this is another example. We've seen a couple of examples in the section, and here's another example where it helps to think about what's happening slightly to the left of 2, numbers like 1.9, 1.99, and numbers slightly to the right of 2, 2.1, 2.01. And as with some earlier problems, we're going to feel free to be a little vague about it, to be a little hand-wavy about it. Although we have the formal definition of a limit, we're mostly talking our way through it rather than writing down formulas. Okay, so what happens? The limit as x approaches 2 from below of x squared over x minus 2 squared. And the limit as x approaches 2 from above of x squared over x minus 2 squared. Okay, and of course, if those two are equal, then we're in business. That'll be the limit. It could be plus or minus infinity, but anyway, if they're equal, that'll be the limit. If they're unequal, then the limit will be d and e. Or if either one of the two is d and e, then the limit as a whole will be d and e. Okay, so as x approaches 2 from below, the numerator is tending to 4. I know it tends to 4 from below. I'll write that in because why not? But mostly it matters that it tends to 4. As x approaches 2 from below, x minus 2 is approaching, well, let's see, when x is 1.9, 1.99, 1.999, the numbers in here are small, 1/10, 1/100th, 1/1000th, but negative. So negative 1/10, negative 1/100th, negative 1/1000th. When you square them, they become small. Square a tenth and it becomes smaller. Square a 1 over 1/100th and it becomes smaller, but positive. So these are going to be small but positive numbers. As a result, the denominator approaches zero from above. So the fraction as a whole, let's talk about the SIGN. The fraction as a whole has a sign that's positive on top and positive on the bottom. And because the bottom is going to 0, the fraction as a whole goes to infinity. And the result is that the entire limit is plus infinity. Plus, oh, sorry, slid off the side of the page. Plus infinity. And the analysis on the bottom is much the same. The numerator goes to 4. Happens to go to 4 from above, but it doesn't matter to us. The denominator, similar reasoning, goes to 0 from above. And again, analyzing the sign, the SIGN of the fraction as a whole, the numerator is positive and the denominator is positive, so the fraction as a whole, the entire limit is a positive infinity. And as a result, we can say, we summarize the two with the limit as x approaches 2, no above, no below, just 2, of x squared over x minus 2 quantity squared is positive infinity. Okay, let's see here. Pop this back up here. Okay, and pop this off. Okay, this stuff gives me trouble. There we go. I got my background. Okay, so just trying to summarize here how the homeworks are going to go. I'm going to do probably most of them 5, but sometimes I'll feel free to if I have a long one, to do 4 or 3. I will typically include something from a prior section because I'm modeling. That's what you should do. You should always include material from before. Not 4 out of the 5, but maybe 1 out of the 5. Material that came from previous sections that you're just going back and revisiting periodically, trying to make sure that it's really, really in between your ears. And then the other thing, although I didn't need to ask, AI how to do the problem, but maybe some of them through the semester I will, who knows. But if you get stuck, and people get stuck, that's if you knew it all, you wouldn't be in here. If you get stuck, you should, after a minute or two of saying, the difficulty is I just really don't understand what to do in the negative case. After a minute or two of trying to analyze what it is you're stuck on, saying, I have no idea about any of this is not helpful. But after a minute or two of figuring out what is it you're stuck on, go and look for the answer. Flip back through the book, let's say, maybe find an example that's a lot like the thing you're stuck on, or ask AI if you want to ask AI. Then that's a good time to say, oh, I see what to do. In the negative case, you have to break it into numerator and denominator. That's good. So you learned. Of course, if you really get stuck and you just can't figure it out, then it's time to put a big asterisk in your notebook and take that to class and raise your hand and say, I don't see number 15. That's what the instructor is there for. That's exactly the kind of question that I like to get as an instructor. Okay. So for every section now, I'm going to do one of these, and I hope that it's helpful to see some of the problems done out sort of live, sort of by hand. Okay, very good. On to section 2.3 next.